So thanks everyone for coming here. Back to MIT S191 Intro to Computational Thinking. This is our second lecture from the Climate Modeling module, which is the last module of the class. And so we'll start out with a recap in case you missed the last lecture. But I wanted to start everything out by showing this nice picture of our planet. It's probably not a planet you recognize because the whole thing is covered in ice. And this is obviously not a real picture because humans haven't experienced this, but we do think that this has actually happened at some point in Earth's distant past, millions and millions of years ago. And so our task for today is to try and understand how can our blue planet support life and have, a wonderful diversity of climates like we have in present-day Earth and in the pre-industrial Earth hundreds of years ago, while also admitting climates like this that are extremely harsh and tens of degrees colder than today everywhere on the planet. All right, so let's start out with a review of the basics of climate science. So in lecture one, we talked about basically Earth's planetary energy balance, which you can think of either as this equation here or this diagram. And basically there's four different things you need to know. The first thing is that the planet is warmed by incoming solar radiation. This is shortwave visible light and ultraviolet light that comes in from the sun. Some of that is reflected. That's where this minus alpha term comes here. That's going to be really important today because, as we'll learn, ice reflects a lot of sunlight. So then that's what warms the planet, but the planet also has to cool itself down so that it can come to some stable equilibrium, and that's happens through this outgoing thermal radiation. If something has a temperature, it radiates to space. In the last lecture, we talked a lot about how humans add CO2 to the atmosphere, which actually traps some of that outgoing radiation and can cause some extra warming, but we're actually going to ignore that today. And so in the equation, if you basically don't change the CO2, then this whole logarithmic term here just equals 0, and so we don't have to worry about it. And so our model just simplifies to this, where basically warming from solar radiation, cooling to space, and the sum of those two is going to be your change in temperature. So if the sun is warming more than we're able to cool the space, we're going to warm, and if it's less, then we're going to cool. And that's sort of the key equation that we're going to look at. So if you just sort of take this equation at face value in the way that we looked at it in the last lecture, it's quite simple, and that's because it's a linear equation. And by that I mean the change in temperature, which is our state variable here, is just a function of a bunch of constants and a linear, or just the first power of itself. So we call that a linear ODE because basically we can write the change in temperature over time as just a function of temperature itself, where that function is just a linear function, ax plus b. And these linear ODEs are really not that interesting because they only admit one stable solution. So if the change in temperature is equal to 0, as in you're not really changing at all, then there's only one solution that admits that, only one temperature where that happens. And in the last lecture we found that for present-day Earth, that's this pre-industrial temperature 14 degrees C. And so before ignoring changes to CO2, if the temperature changes at all away from that, it's just going to come back right to it. And so that's a stable equilibrium. Okay, so that's the review. Let's get into some of the background for today. So as I said, there's this period called Snowball Earth about 700 million years ago. So there was actually two of these periods. One of them lasted 40 million years or so. The other lasted just about 15 million years. And these were periods where we know from geologic evidence that the entire planet, from the poles all the way to equator, was covered in ice, like this reconstruction picture suggests. Okay, so let's talk about some of the physics as to why we think that might have happened. So I want to focus on this parameter alpha, which is the reflectivity or the albedo of the planet. And so in the last lecture, we talked about how this is basically just a constant value for small changes in climate. And the reason is that the oceans cover most of the planet. Most of the oceans are liquid. They're this kind of dark bluish thing, and they absorb a lot of radiation. And clouds are pretty bright, and so they reflect sunlight. Clouds aren't really changing all that much. And so you can pretty much get away with just setting this alpha to be a fixed value, 0.3, or 30% of incoming solar radiation reflected to space. However, when you start thinking about really big changes in climate, where maybe, say, the whole ocean is going to freeze over, you're now going from a really dark ocean, which has an albedo of about 0.05, so only 5% of the incoming radiation is reflected by the ocean. When you freeze that over, you get ice and snow, which has albedos of 50% to 90%. So actually, most of the radiation that comes in and hits snow or ice is going to get reflected right back to space. So we clearly can't just let this alpha be a fixed value. We're going to have to make it be a function of temperature, for example. And so what this does is it actually introduces a nonlinearity, as we'll see, and this allows for nonlinear positive feedbacks. And you can think of these as sort of reinforcing cycles. And so that's sort of what this looks like. Imagine your planet, you have a little bit of warming. That's going to lead to some of the ice melting. That's going to mean that there's more ocean exposed, which has a low albedo. It's going to absorb more sunlight, and that's going to also lead to more warming, which is going to melt more ice, et cetera, right? This is going to go on and on and on until you've melted a whole bunch of ice. And this is sort of schematically shown here in Antarctica in white. Okay, so the simplest way of doing this is to say, okay, we're not going to know exactly how much of the planet is covered in ice at any given time, but let's just say if the temperature is much less than the freezing point on average over the whole planet, then let's just give it the albedo of ice. And if it's much warmer than the freezing point, so say 10 degrees C, let's just say there's no ice. So we have these two states, no ice or a lot of ice with different albedos, and let's just linearly connect the two to cross through the freezing point. So that gives us a graph that looks somewhat like this. So you have this region for less than minus 10 degrees Celsius, where it's completely frozen, really high albedo, a lot of radiation is getting reflected. For warm climates, you have no ice, a lot of the radiation is getting absorbed, and then there's this region in between where it's called partially frozen. All right, so what happens if we now add this? All we do is we just add this temperature-dependent albedo function into our model. So how do we do that? So first, we just code up this function. So it depends on temperature. That's a required argument. And then we have these other optional arguments, which, if we want, we can change how bright ice is, for example, or how large this range of the partially frozen range is. But basically, we just have three if statements, right? If it's really cold, it's ice. If it's really warm, it's ocean. And then we have this thing in between, which is just a linear curve. All right, so now that we've got this function, we can just stick it into our model. I've hidden this cell here, but I've just copy-pasted a bunch of the climate model modules and functions from the past lecture. And all we're going to do here is the only thing we're going to change is we're going to slightly update this time-stepping function, which we saw last time. Basically, what it does is it takes our energy balance model type, and actually, I don't even need this here. And all it does is it takes the temperature and it time steps it forward, adding the change in temperature, and it steps forward time as well. And the only thing we're adding here is that we're saying at every time step, we want you to override the albedo in the model with this temperature-dependent albedo. And so if the temperature changes such that some of the ice melts, it's going to incorporate that by changing the albedo here. All right, so let's run that, and now let's look at what happens. And so basically what we're going to see in this section is that this is now going to permit multiple equilibria. And if you saw Dave Sanders' lecture on Tuesday on sort of nonlinear dynamics and fixed points, basically these multiple equilibria you can think of as multiple fixed points. And we'll see that there's both unstable and stable ones. All right, so let's put this into our model and see what happens. So for reference, in David Sanders' lecture, you saw these equations like x dot equals mu plus x squared. Think about this being the same thing, except now x is temperature, and mu might be solar insolation, for example. And x squared is the temperature-dependent albedo term. All right, So here's sort of how this works out. All we're going to do is create an instance of our climate model with some initial temperature T naught, and we're going to start it in year 0 with a time step of 1 year, and we'll just say that the CO2 is constant for now. And then we'll just run it forward for 100 years, and that's plotted here. So let's say we start out with 30 degrees C. What's going to happen is, this is basically the same case we saw in the last lecture. So you're just going to cool down until you get to this pre-industrial value of about 14 degrees. And that's going to happen for basically all temperatures greater than 14 degrees. And if you're right at 14 degrees, that's the equilibrium, and so it just stays there, right? That's not super interesting. And the same thing as last time happens if you go to colder than 14 degrees. It's just going to warm up a little bit until it gets back to 14. It gets sort of interesting now once we start dropping below 10 degrees. So you'll notice that even for 8.25 degrees, we're starting out in a region where we have partial ice cover. It's not greater than 10 degrees, so there's still some ice, but the ice albedo feedback's not quite strong enough to overcome the incoming solar radiation, and we're still going to warm up and reach that no ice equilibrium state. But if the temperature drops a little more to below 7.5 degrees, we see that actually we don't keep our no ice. Even with just a little bit of ice, we're now going to shoot down into this frozen state, the snowball state. And indeed, for any temperatures less than about 7.5 degrees, we end up with this equilibrium down here, completely frozen with very cold temperatures of minus 40 degrees. And so that's what we mean by multiple equilibria. For the same exact equations, you can have basically 2 of these equilibrium states and some transition in between the 2. And so that's sort of what happens if you sort of step through these things. But you can also plot just a whole bunch of these classes of curves. So here I just started, I think every 5 degrees I started one of these curves. And you can see that you have this top branch where it goes to 14 degrees, and this bottom branch where all of these temperatures go to minus 40 degrees. But then we see something kind of interesting right in the middle. We have this other branch where if you give it exactly the right value of like 7.543 something degrees, it's going to stay right there forever. But if you give it just a slightly different temperature, where you start just 1/100th of a degree away, you can't even see that difference on this plot, then it's going to actually shoot off away from this unstable equilibrium and go towards one of the other 2 stable equilibria. And so these are sort of the dangerous transitional climates where just a tiny change in temperature can send you careening off towards a totally different climate. And so we'll sort of look at some of the more interesting implications of this later on. All right. So dynamical systems theory gives us a really nice language for trying to understand why these transitions happen and why these equilibria exist. So let's think about that. So our energy balance model is, again, just the change in temperature equals the ASR, which is now a function of temperature, and the outgoing thermal radiation, which is also a function of temperature. So one thing we can do is, if we know what this is and we know what this is as a function of temperature, we can just plot both of them as a function of temperature, and then when this one is bigger than the negative one, we're going to get warming, and vice versa, we're going to get cooling. So let's do that. And so here we're just going to sample a whole bunch of temperatures. So we'll go from minus 60 to 30 with a step of 1 degree. And then we'll just take our equation, or our function for the outgoing thermal radiation, broadcast it across all the samples. And same thing for the absorbed solar radiation, although we have to be a little careful here because this alpha function I didn't write so that it broadcasts. So I have this list comprehension thing going on. But basically we just have these 2 arrays, and now we can look at the imbalance, just absorbed solar radiation minus outgoing thermal radiation. And that's plotted here. So right from minus 60 to about 40 degrees, we see that you have more radiation coming in from the sun than you're emitting to space. But once you warm up past that, then you're starting to efficiently emit radiation to space, and so you can cool back down again. And so there, you're cooling off more than you're absorbing from the sun, and so you're going to end up cooling. Here you're going to end up warming, and then out here you're going to end up cooling again. And we can look at that a little more clearly if we just subtract the two and calculate the radiative imbalance, which is basically this C, the CdT up here. And so indeed, for temperatures less than 40 degrees, you're going to end up warming. For temperatures between minus 40 and this unstable equilibrium, you're going to end up cooling. And then between these two, you're going to warm, and then large temperatures, you're going to cool again. And so let's just think about what would happen if you started out somewhere like minus 50 degrees. So it's minus 50 degrees, you start here, but you're receiving more solar radiation than you're emitting, and so you're going to warm. And so we can sort of travel to the right on this curve because x-axis is temperature. So we travel to the right, and now we reevaluate, and we're still going to warm because we're still absorbing more than we're emitting, so we're going to warm more until we get to here, right? And now if we try and warm a little more, we're going to go to here, but now we're starting to cool again. And so now we cool back. And so basically, if you depart from this aqua circle, you're going to come right back to it. So that's a stable equilibrium. Same thing for this orange one. If we go up here, we're going to cool. If we go up here, we're going to warm. So we come back to orange. What's interesting is now if we start out at the gray one, if we cool just a little bit down to here, well, now we're going to keep cooling. And so we're going to keep going, keep going, keep going. And if we get to here, we're going to still keep cooling, keep cooling, keep cooling until we get all the way to this state. And so you can sort of think about, this region is stable, unstable, stable. Okay, so how does this sort of matter for this snowball Earth problem we were talking about? Well, things haven't always been the same on planet Earth over the last 700 million years. One of the things that has changed is that actually the sun has gotten brighter. So this is a plot which shows the brightness of the sun relative to today. So a value of 1 is the present day brightness, and 0.7 is 70% as bright. From the beginning of Earth's history, 4.56 billion years ago, to present. And what we see is that the sun has brightened about 40% since then. And even since just 700 million years ago, the sun was only 93% as bright as it back then as it is today. And so we would expect that it should be a little bit cooler back then relative to today, because the sun was just less bright. And we can pick that exact value of the solar radiation, and we can plug it into our model and see what happens. And so let's do that. So if we plug that into our model, we start out here in this black dot, where the solar radiation is up here, 1,272. So what happens now if we slightly warm up the planet a little bit? So if we warm up just a little bit to now 1320, let's say this is like 300 million years ago, we're going to warm up a little bit, but just by a couple degrees, the planet's still going to be really cold. So what if we now try and fast forward all the way to the present, which is this yellow strip here? That's the present day insolation. So today, or in the pre-industrial climate, we were getting about 1,380 watts per meter squared was the incoming solar radiation from the sun. But in this model, what happens is the temperature is really cold, right? We've only warmed about 10 degrees or so since 700 million years ago, and the planet is still completely frozen. So that's kind of weird. So what would happen if we tried to brighten the sun even more just to make up for that, right? What we're trying to do is get to here. We want a planet that's a lot warmer. So present day is about 14 degrees C. There's very little ice on the planet. We want to get there. But if we keep, oh, okay, something happens here. When we get to a certain amount of solar radiation, what happens is you're no longer completely frozen. You start getting temperatures that are partially frozen, and then the ice albedo feedback kicks in, and we warm really quickly up to, this is like extremely hot. This is 60 degrees Celsius, hundreds of degrees Fahrenheit. And now we're sort of up here, and now what happens if we try and cool back down again? Well, then what happens is, even when we cool back down to today, we get the right temperature. We get back to 14 degrees C. So that's weird because we just saw that before we had the same amount of insolation. The sun was just as bright as it was down here, but now it's a lot warmer, and that's because there's no ice at all. And indeed, if we cool down or we turn down the sun relative to today, boom, we're going to shoot right back down to the Snowball Earth. And so, if something happened today and all of a sudden the sun was 70% as bright, this is probably what would happen. Over the course of a few hundred years, we would plummet back into a Snowball Earth state. All right. So it's kind of this interesting dynamic where there's this sort of path dependence in the climate system, right? It depends what direction you're going. If the sun is brightening, you can warm up like that, but then if you cool it back down to the same amount, you don't go right back down, right? You're sort of stuck on this thing until you get it cool enough that the ice starts forming, and then boom, you go down to the cool spot, and then you don't get back to warm until you get to this white region, and then you can melt the ice again. So that's this sort of bifurcation diagram that we saw in David Sanders' lecture. All right. And so just to sort of really make the comparison with other nonlinear dynamical systems even clearer, we can add in these branches, which actually show the stability branches. Right, this is the stable branch for cold temperatures, this is the stable branch for warm temperatures, and this is the unstable branch. So if you started in sort of this triangle, you're going to shoot up to this warm one. If you start in this lower triangle, you're going to shoot down to the Snowball Earth. And indeed, we can sort of see that when we actively change the solar radiation, we are going to change along these lines. And so that's sort of how dynamical systems theory can be really helpful for climate is. These kinds of plots show up all the time in the climate system. All right. So if people have questions about the climate science, I'm happy to do that. Or you can also follow up with questions on Discord or in the YouTube chat. So these kinds of nonlinear transitions happen all the time in the climate system. So if you just look at a record of temperature going back 60 million years, you see these variations where, in just a few thousand years, you get this rise in temperature of a few degrees. A million years ago or so, you used to have these ice ages where every 100,000 years you plummet down into a mostly frozen state and then it warms up again. And then, of course, now, for very different reasons, we're emitting greenhouse gases and we're going to get a very rapid warming. So note that this x-axis here is logarithmic. So this is 10 million years here, whereas this is just 100 years in the future. So yeah, the takeaway here is that we're changing the climate possibly in the next 100 years about as much as has changed in the last few million years. Okay, so let's get back to our problem. So we saw in this graph here that when we start out with the Snowball Earth 700 million years ago, where it's completely frozen, there's ice everywhere, so it's reflecting a lot of sunlight to space, which makes everything really cold. If we try and warm up to the present day amount of solar brightness, the temperature doesn't go all the way to the present day value. It still stays really cold. So what gives? Why, how did we end up actually getting out of the Snowball Earth? How do we get to today if we, the sun has never gotten so bright that we were able to shoot up like this? So this is still sort of an open question in climate science, but the leading theory is that it has to do with CO2. And so this is sort of what the argument is. So let's start here. So you have this climate where you've got some ice on the poles and you've got some continents with volcanoes. And let's just say that it starts getting a little colder, and so the ice albedo feedback kicks in and it starts freezing the planet over, so you get this. And so now what's going to happen is you have an ice-covered planet, really high albedo, emitting to space, is reflecting a lot of the radiation, incoming solar radiation to space, and so it's going to cool the planet, and you're just going to have this really cold planet. But what's going to happen over time is that the volcanoes don't stop. They keep erupting beneath this sort of frozen tropical equator. And so what we think is that basically when these volcanoes over millions of years are just exploding and exploding, they're releasing a whole bunch of CO2 into the atmosphere. And so we think that this carbon dioxide is just accumulating in the atmosphere for millions of years until there's so much of it in the atmosphere, such a strong greenhouse effect, that it can overcome the reflectivity of the ice and melt it all back down. And so what happens is that then the ice melts pretty much immediately because the ice albedo feedback kicks in the other direction and helps you melt the ice. But now you're stuck with a climate where you've melted all the ice, so now your oceans are really dark and absorbing all of the incoming solar radiation, and you have a ton of CO2 in the atmosphere. And so that's how you shoot back up to these really warm climates that are like 50 degrees C. And so we think that's sort of what happened in the past and is how we got back to today. Eventually the CO2 went and got stored in the oceans, and we sort of ended up with today's climate, where you have small ice caps at the poles and a big ocean and a little bit of CO2. So actually homework 9 for those who want to do it is going to be all about this problem. So you're going to basically do a lot of the same analysis that we did in the lecture today, but you're going to look at what happens when you add CO2. So here we just fixed CO2 at the pre-industrial value of 280 parts per million. In the homework, you're going to increase CO2 and see how much CO2 would you have to add to the snowball for the ice to melt. All right. So then I just want to add by saying that this is a really simple model, but this stuff also happens in more complicated climate models. So here's this example of what we call an aquaplanet, which is a 3-dimensional planet now, but completely covered in ocean. So it's unrealistic in that aspect. But what happens is if you start here, so the colors on this orb here are the temperatures. Red is warm, blue is cold. And on the x-axis here is time. And so this red curve is slowing over time. And so, is the solar constant, or the solar insolation, is cooling over time, so it's less and less bright sun. And eventually what happens is the ice albedo feedback kicks in and you grow an ice cap. And you have this frozen ice that's really reflective, but it doesn't go all the way to the poles. You don't get a full snowball Earth. You get this sort of water belt world in between the two, which is kind of similar to today if you think about it. But then if you cool down a little more, if you keep decreasing the brightness of the sun, you do get a snowball Earth, right? Eventually you do transition here all the way to a snowball Earth. All right, so that's pretty much it for today's lectures. So thanks everyone for coming, and I'll hang around for maybe a couple minutes and answer questions in the chat. Otherwise, we have now the closed session with the MIT students. So thanks a lot.